So this is a review question from our last meeting, which would have been last Monday. We have 100 grams of water and 25 grams of sodium chloride. What we want to know is what is the vapor pressure of the sodium chloride solution at 25 Celsius. Now the normal vapor pressure of water at 25 Celsius is 23.8 torr. We need to figure out what the vapor pressure of this substance is, of this solution. All right, let's try to work our way through this here. So we've already been given, we're trying to find the pressure. We've already been given the normal vapor pressure of water at this temperature, is the 23.8 torr. So what we need to find is the mole fraction of water. Now remember, the mole fraction of water is going to be equal to the moles of water divided by the total moles in the solution. So what I need to do is I need to figure out how many moles of each substance there are, put them together, that's my total moles, and divide that into the number of moles of water. So I have 100.0 grams of water. There are 18.02 grams of water in a mole. So 100 divided by 18.02, the four significant figures would be 5.549 moles. And the 25.0 grams of sodium chloride, molar mass of that is 58.44 grams of sodium chloride in 1 mole. So 25 divided by 58.44 would be the three significant figures, four, extra zero there, 0.4278 moles. Add those two together, and I get to 3 decimal places, 5.977 moles total. So the mole fraction of water, 5.549 moles, divided by 5.977 moles. 5.549 divided by 5.977, the four significant figures, 0.9284. Remember, mole fraction is a unitless concentration. I have moles divided by moles, so they cancel out. So that value times 23.8 would give us to 3 significant figures. The pressure of this solution would be 22.1 torr. And again, in context, this all makes sense. We know that vapor pressure is going to be lower by the presence of a solution, so this is lower than what it was. But we also know that it's relative to the concentration. 25 grams of sodium chloride seems like a lot, but it's not even 8% of the moles of the solution. So it doesn't make that big of a difference after all. Any questions with this problem, this review, before we move into our last two concepts out of chapter 11 here? So I've got another question for you to lead into that. Kind of already know the answer to it because we did a lab about it, and we have kind of been talking around this concept for about a week or so. But how would we expect the freezing point and the boiling point of a solution to be relative to the solvent that makes them? So if I'm looking at water, what is its boiling point normally? 100 degrees. What is its freezing point normally? 0. Now, if I take that water and substitute it a solution of sodium chloride, like in the last example, how do I expect that 0 and that 100 to change? So take them in pieces. How do I expect that freezing point to change? Is it going to get lower? Is it going to get higher? Or does the sodium chloride in solution not make a difference? Same thing with the boiling point. Does the boiling point make it higher, lower, or no change? All right. Now, most of you are on the right track. And certainly, with all of this talk about the boiling point, or excuse me, the vapor pressure coming down in solution, the first part is pretty easy to rationalize. We know that the boiling point is going to rise. And most of you had that. We talked about it at length last Monday as well. We talked about it previously in chapter 6. The extra intermolecular forces bring the vapor pressure down, and so the boiling point is going to go up because boiling occurs when vapor pressure and atmospheric pressure meet. And since the atmospheric pressure isn't changing, but the vapor pressure went down, it's going to require more energy to get that vapor pressure back up to atmospheric. That all makes sense. The one where we're a little bit lost is that freezing point depression, which is okay. We hadn't talked about it yet. You did a lab on it on Thursday, but oftentimes we do labs and we don't always necessarily fully understand exactly what we're doing. We just collect the data and we kind of go, and we work our way through the calculations without really giving a whole lot of thought to what it is that we're calculating. Well, now we've got the context. The solution is going to freeze at a lower temperature because the intermolecular forces between the solvent and the solute particles also are stronger. So really, here's what intermolecular forces do in the liquid phase. Stronger intermolecular forces cause liquids to stay liquids longer. Because as soon as we go into the freezing, those intermolecular forces are going to change because you're no longer going to have that fluid mobility of those substances moving around. They're going to be locked in place because of the nature of the solid. So the greater the intermolecular forces are, the more liquid that phase diagram is going to show. And we can see that in the phase diagrams of solutions themselves. So I'm going to do my best here to draw what the old phase diagram looked like here in, let's go with blue. So the old phase diagram looked like this. That was the old phase diagram of water. And what we can see is that by changing from just pure water to a solution, that liquid to solid line moved backwards. And that liquid to gas line moved forward. So our new phase diagram for this solution features a much more prominent, much larger liquid section than the phase diagram of the solvent by itself did on its own. And so we have a term for those changes. We call this the freezing point depression. Because we can see how much that freezing point has been depressed, how much it has been lowered by going into solution as opposed to on its own as a solvent. And over here we have the boiling point elevation. Because we can see how much that boiling point has increased as it went from solvent to solution. So everything has moved as a result of these extra intermolecular forces. Now, what's remarkable about these two phenomena is that we can treat them pretty much the exact same way in terms of calculations. Freezing point depression and boiling point elevation, because they are so temperature dependent, they are both relying on molality as their primary concentration unit. But like we saw with osmotic pressure, that molality does have a caveat attached to it. We're talking about total concentration. So I do need to consider the Van Hoff factor I in these calculations as well. Remember, the Van Hoff factor is that correction that we put on concentration if our solution gives us multiple particles per molecule, which we really look at in terms of if the substance is ionic, how many ions does it give us? So total molal concentration is the one factor. The other factor is something called K. Now, this is one of our first exposures to the letter K in this class. There will be many, many others, especially if you take Chem 106. You will get sick of the letter K by the end of that particular class. K is a stand-in for pretty much any constant that we have. And so the constants here, Kf and Kb, refer to specific values associated with the solvent itself. And the values of Kf and Kb have a lot to do with what the intermolecular forces are inside of those solvents. So these are values that would be assigned or given to you. Or in the case of your lab, knowing some information, you can actually calculate the value of K if you know the concentration, if you know the temperature drop in the case of freezing point. So these equations end up being really easy to use once we know what we have. And the fact that they're practically identical to each other, the only thing that changes is the value of the constant, depending upon what solvent we're using and whether we're looking at something boiling or something freezing. Those are really the only differences between these calculations. Now, taking a look at some examples. We can see that our value of Kf and Kb do have a lot to do with intermolecular forces. The numbers that are smaller tend to be ones that have greater attraction to each other. Not always a given, not always quite a great look, but it's a good general rule of thumb. We know that water and ethanol have the strongest intermolecular forces of these five. They also happen to have the smallest Kf and Kb values. So what we can look at also is here is a bank of normal boiling points for the substance, normal freezing points. And these are how much they are affected by the concentration. So what we can see is that as the concentration increases, the effect on the temperature is going to be considerable. So for water, every mole of concentration will raise the boiling point by half a degree. Will lower the freezing point by about 2 degrees almost, 1.86. Whereas for other substances, that effect is going to be a lot greater because the strength of the intermolecular forces is going to be a lot more noticeable. If you have weak intermolecular forces to begin with, and we've just intensified and strengthened them, we're going to see a much bigger impact. All right, let's take a look at an example. What is the boiling point of seawater, in which the concentration of sea salts is equivalent to 0.560 moles of sodium chloride per kilogram of seawater, and the Van Hoff factor is 1.85. All right, the equation that we have to use here, since we are talking about boiling point, delta TB is equal to I times KB times the molality. I, the Van Hoff factor, we've been told is 1.85. To find Kb for water, we need to go back to the previous slide. Kb for water is 0.51 degrees Celsius per molal. So 0.51 degrees Celsius per molal. And we're told that the concentration is 0.560 moles per kilogram. Moles per kilogram being the definition of molality. So we can insert that one appropriately here. Do my calculations, molality cancels. All that is left is degrees Celsius. So my boiling point temperature, or excuse me, my boiling point elevation, 1.85 times 0.51 times 0.56 to two significant figures is 0.53 degrees Celsius. Now, important thing to note right here. We are not done with this calculation. Remember, the question has asked, what is the boiling point of seawater? If I stop right here and put in 0.53 degrees Celsius, what I am saying is that the addition of all of that salt in the water has caused the boiling point to drop by 99.5 degrees. That's not what we mean. Remember, this only gives us the elevation. This only gives us how much it went up. We still need this last step. Boiling point of water is usually 100 degrees. We're adding the 0.53 to it. So the actual boiling temperature here is 100.53 degrees. We can't ignore that little extra step. And I will tell you, this is going to be the most common mistake in that chapter 11 quiz. Won't be the most missed question. The most missed question will be the conversion between molarity and molality. It always is. But in terms of which mistake was the dumbest that we could have prevented, this would be it right here. Same thing for freezing point. If you don't subtract that freezing point depression from the normal freezing point, you haven't done the full problem. All right, any questions with this example? All right, let's take a look at a little bit more complicated of an example. We've got sodium chloride, which we are using to melt ice on sidewalks after a winter storm. Question is this: could calcium chloride melt ice at -20 Celsius? We have to assume that the solubility of calcium chloride is 70 grams per 100, and that the Van Hoff factor is 2.5 for a saturated solution. Okay, now with a problem like this, there are multiple ways of attacking it. One method to attack this kind of problem would be to simply work backward. Look at that 20-degree drop in freezing point. Use it to work back to figure out what the concentration of the calcium chloride would have to be to get to -20 and compare. One way to do it, perfectly valid. The way that most of us would go about it, however, would be to convert that concentration into molality and using the freezing point depression to figure out what the freezing point would be. Now for that, not too difficult to do. We've already been given a concentration. We just need to modify it a little bit. So 70.0 grams per 100. Well, we can change that. Grams of calcium chloride per 0.1 kilograms of water. So now we've got the denominator in the proper unit, kilograms. All we had to do was convert the grams to kilograms. No big deal. And then to turn it into molality, got to look at that molar mass of calcium chloride. Calcium is 40.08. Chlorine is 35.45, and there are two of them. So 110.98 grams in 1 mole. So 70 divided by 0.1 divided by 110.98 would give us 6.31 molal as the concentration of calcium chloride. From here, now it's just a freezing point depression problem. Delta TF is equal to IKFM. I, we are told, is 2.5. KF, we are told, is 1.86 degrees Celsius per molal. Concentration we just calculated, 6.31 molal. So our freezing point depression, 2.5 times 1.86 times 6.31 to two significant figures because of the 2 in the Van Hoff factor is 29 degrees Celsius. Now again, easy mistake to make would be to assume that this is it. 29 degrees Celsius, I look at that and say, okay, 29 degrees Celsius is nowhere near negative 20. This isn't going to work. We have to remember to subtract. Normal freezing point of water is 0. We subtract 29 from that. This particular solution would freeze at negative 29 Celsius, which means that that negative 20 degrees Celsius ice wouldn't be ice at negative 20. It'd still be in the liquid phase with all of this salt on. So again, there are multiple approaches to this problem. You could have worked it the other way, figured out what the concentration would have been to get that negative 20 exactly. But this works just as well. All right, any questions with this example problem? Okay, so that was boiling point and freezing point. That was the last of the colligative properties. The only other thing that is left out of chapter 11 to talk about is this, Henry's law. And I'm going to warn you, Henry's law, we don't need to know nearly as much about it as what your book tells you. Don't even worry about copying down that equation. We're not going to calculate Henry's law in any kind of way. What Henry's law concerns is the solubility of gases in solution. And it's a relatively simple relationship. The higher the pressure above the solution, the more soluble the gases are. That's it. The higher the pressure, the more soluble the gas is going to be. Now, one other thing that Henry's law addresses is the fact that solubility is temperature dependent. When we increase the temperature, the gases will naturally, through their own molecular motion, find their way out of the solution. So if we're trying to dissolve gas into water, gas into any liquid, two things need to be present. It needs to be cold, and we need to have a good pressure above. Best example of that is this, a bottle of soda. In a bottle of soda, you've got both of those conditions present at the same time. because that bottle, when it was bottled, is bottled under high pressure in a cold atmosphere. Why is it done that way? So that it's fizzy when you open it. And so, as soon as you open that bottle, what's the first thing that happens? Hear all the gases starting to escape. All that extra pressure that was put in on top to keep that carbon dioxide inside of the soda, well, that pressure's been released. And so what do you see? You see a whole bunch of bubbles forming inside of the bottle, and they start making their way out. Why? They're not dissolved anymore. And so they eventually start to make their way out, which is why a bottle of soda is really only good for a little while. As soon as you open it, the pressure gets released, it's done. If it was warm in the first place, it goes flatter a lot faster. If it's warm and you leave it out on the counter all day, it's going to be flat by the time you get to it that night. That's what you need to take away from Henry's law. Don't get bogged down in the calculations. Don't get bogged down in all the extraneous stuff. Think about the relationships. Conceptually speaking, what are the two factors that involve solubility of gases? Temperature and pressure. That's all you need to know.